This video is about timing and synchronization when crossing clock domains. Remember the scenario? We have an outside signal coming in from another device. It could be a human pressing a button. It could be another device operating on a different clock. Because we cannot control when that signal changes, there's a distinct possibility that the input to this flip-flop changes too close to the rising edge of our own clock, causing this first flip-flop to become metastable. The way we've learnt to deal with this with a single bit of input is to use two flip-flops cascaded like this. In the olden days, when flip-flops were slower, you could use 3 or more such flip-flops. We'll understand why a bit later. Remember what happens when the first flip-flop becomes metastable. If its output is normally 0 volts for a logic 0, or say 5 volts in the olden days for logic 1, then if it's in its metastable state, it means its output is halfway between these two values, or at 2.5 volts. But this is an unstable state that it's in. We'll learn another day why it's an unstable state, but for now we just accept it's a bit like trying to balance a broom inverted on your fingertip. It's going to fall over quite easily. And so what happens is that if the flip-flop does become metastable, sooner rather than later it will exit either to a 0 or it might decide to exit to a 1. We have no idea which way it's going to exit in practice because it's influenced by the randomness of thermal energy and other such factors. In order to understand why double flip-flop synchronizers work, we need to understand when a flip-flop will exit from its metastable state from a probability perspective. Remember, it's a random process driven by randomness such as heat in there. Without going into the physics, the key property is that if a flip-flop is already in the metastable state, it doesn't matter how long it's been in the metastable state, the probability that it will exit in the near future is the same, irrespective of what's happened in the past. And this means that we can model it via a very simple idea. We're going to take our timeline. Let's assume that our flip-flop becomes metastable at time t equals to 0. And we're going to break time up into small units of time. Doesn't matter how small, doesn't matter how big. But from what we said before, we can assign the same fixed probability that the flip-flop will exit from its metastable state in the first interval, or the second interval, or the third interval, or the fourth interval, and so forth. Now, the size of each interval will help determine the probability that the flip-flop will exit from its metastable state. But let's assume, for concreteness, that we have a probability of 1/2 of exiting from our metastable state after this period of time. If you'd like a definite period of time, you can assume it's 10 picoseconds from here to here, just for concreteness. So the probability that we will have exited after 10 picoseconds is 1/2. What's the probability we would have exited after 20 picoseconds? Well, if you like, there are 4 things that can happen. This probability 1/2 we can recreate by tossing a coin. In this first period here, we toss a coin. If it comes up heads, we say we've exited from the metastable state. If it comes up tails, we're still in the metastable state. So we toss a coin. If it's heads, then we've exited. We're done. If it's tails, we stay in the metastable state and we have to toss our coin again. If it comes up heads, then it means we exit in the second period. If it comes up tails, then we stay in the metastable state for the second period and we toss the coin again to see if we come out in the third period. Now the key point of this diagram here is that out of all the 4 possibilities of tossing a coin 2 times in a row, only 1 out of the 4 possibilities leads to us being stuck in the metastable state after 2 cycles. So that means that with probability 1/4, we are still stuck in the metastable state, or, in other words, with probability 3/4, we will have exited after 2 cycles. Now, after 3 cycles, we do the same, and we find that the only way that we are stuck in the metastable state after 30 picoseconds is if we toss 3 tails in a row. And that's got probability 1/8 of happening, which means with probability 7 on 8, we will have exited after 30 picoseconds. Now, if you're not seeing a pattern here, then imagine the probability of still being in the metastable state after 10 periods of time. That means we've tossed a coin 10 times and it's come up tails every single time. And you can see that the probability of that happening gets smaller and smaller very, very fast. And this is why we're going to exit from a metastable state with a high probability after a certain period of time. Think about how many coin tosses you think would be very hard to come up tails continuously, and you can be almost certain that we will have exited from the metastable state after that period of time. Let's do a specific calculation. Let's say that we have a 50% chance of recovering from our metastable state after, this time, let's make it 100 picoseconds. And then the same calculations apply as before. That means that after 200 picoseconds, the chance of recovery is 75%. Now, what about after 20 nanoseconds? Note that 20 nanoseconds is the period of a 50 megahertz clock, the same clock frequency that we're using on our DE1 SoC board. So we're very interested to know when we have got our double flip-flop synchronizer being driven by our 50 megahertz clock, what is the chance that this first flip-flop will exit the metastable state within 1 clock period? Of course, I'm just making up this number 100 picoseconds, but it is in the ballpark of realism. 20 nanoseconds is 200 times our interval, 100 picosecond interval. So therefore, the only way that we can still be in the metastable state after 20 nanoseconds is if we tossed our coin 200 times and it came up tails every single time. Now we can actually calculate the probability of this occurring, and we find that the probability is less than 1 chance in 10 to the power of 60. Now, this is such a big number that it can be a little bit hard to understand. Let's try to put this into perspective. Let's assume our flip-flop becomes metastable once every second. How many seconds are there in a year? Well, it turns out that there's less than 10 to the 8 seconds in a year. And we have a chance of 10 to the 60 of something going wrong. 60 is so much bigger than 8 that for all intents and purposes, we can assume that our flip-flop will always have recovered from its metastable state before the next clock cycle. With that said, we should not simply dismiss the potential for metastability. I mentioned the flip-flop becoming metastable once a second, but it actually depends on how fast the incoming signal can change relative to our clock frequency. Maybe our flip-flop does become metastable much more often than once per second. Also, I just pulled 100 picoseconds out of the air. Maybe it takes a lot longer for a flip-flop to recover. So Quartus will actually analyse this for us. It's a statistical calculation, but nevertheless, if we ask Quartus nicely, it will tell us for a given circuit what the chances are of a flip-flop becoming metastable under a certain set of assumptions. And let's assume hypothetically that Quartus tells us that our flip-flop will become metastable once in 1,000,000 years. In other words, once every 1,000,000 years, we can expect to have one metastable event on average. This might sound like very good odds. If I've just built one device for myself, then I can be confident that it should just work. But what if the device I've built goes into every single car in the world, and there are millions of cars in the world? That means that on average, someone around the world is going to experience a problem with their car on a regular basis. If there's 1,000,000 cars, then one person might experience something once a year. If there's 365 million cars, then someone on average might experience a problem once a day. So this is not good if that device is serving a critical purpose, such as controlling the airbag. That would be a disaster. Now, if it just concerns the tuning of your radio, it might not matter so much. So metastability, when we consider whether or not it's a problem, we have to consider how many products there are and what are the consequences of something going wrong. I have here a timing diagram that we're going to fill out. So up the top here, we've got our double flip-flop synchroniser. The clock is a regular clock. Don't ask me why this period's a bit longer here, it should be regular. The input is going to start off a 1 and then transition to 0. And the output of the first and the second flip-flops are going to start off at 0. There's a rising edge of the clock, so the first flip-flop takes a photograph and its output changes to a 1 soon after that rising edge. Now, if we're being precise, which we should be, we actually know that what happens is that first there's a period of time straight after the rising edge when the output doesn't change. Then there's a period in between the contamination delay and the propagation delay when we don't know what the output's doing. And then after the propagation delay is up, we know that the output is the correct photograph of the input. So therefore the output of Q1 is going to look like this. And that continues on all the way up until the next rising edge. The second flip-flop does the same thing. Between setup time before the rising edge and hold time after the rising edge, it photographs its input. Now its input is 0. It is already 0, so we can safely assume that it's not going to change. I guess in theory, from what we've said, that the output between the contamination delay and the propagation delay, something might happen, but in fact we know how flip-flops are made. We know that if the input hasn't changed, the output's not going to change, so we can safely draw it like this. At the next rising edge, the first flip-flop photographs its input between setup time before the rising edge and hold time after the rising edge. The input to the first flip-flop is a 0, so therefore the output Q1 is going to, for the duration of the contamination delay, it's going to stay constant. Then between contamination delay and propagation delay, it might change. Who knows what it's going to do in there. And then once propagation delay is up, we know that it's going to be equal to what its input was equal to when it took the photograph, which was 0. Similarly, Q2 is going to, straight after the rising edge of the clock, not change for a period of the contamination delay. So it's going to stay constant. Then the contamination delay is going to kick in until the propagation delay has expired. And now I'm drawing this already because I know that it's actually going to transition. The reason it's going to transition is because around the rising edge, between setup time and hold time, its input is given by Q1. And we see that Q1 around this rising edge is a constant 1. So that the second flip-flop is going to photograph the value 1, and therefore its output is going to change to be value 1 once the propagation delay has expired. Then we come to this last rising edge. The input has not changed to flip-flop 1 between the previous rising edge and this rising edge, so this does nothing. However, the input to the second flip-flop has changed. At the previous rising edge, the input was a 1. At this rising edge, its input is a 0. So the second flip-flop, whose output is Q2, is going to make a transition, same as before. For the contamination delay, nothing happens. In here, we don't know what happens, fill it up with X's, and then it's going to be a 0 after that. And so therefore, what we find is that if we put this input signal into our double flip-flop synchroniser, what we're going to get out is going to be this signal here, well technically with some don't knows in there. Since we had assumed that initially everything was 0, we can assume that in was initially 0 here, and so in effect our input contains a pulse and our output contains a pulse, and we see that it's been delayed. Now this delay has got nothing to do with metastability whatsoever. There was no metastability occurring when we did this timing diagram. It's a simple fact that we are only watching the input at the rising edge of the clock, so we will never find out exactly when the input changes. There will always be a delay between the input and the output. This is an important point in working out why the fact that if we do have metastability, it doesn't actually change the fact that this circuit still normally works as intended. We'll discuss that later. But the point is, whatever circuit is on the right-hand side, it can never rely on knowing exactly when the input changed. There's always going to be some delay, up to 1 clock cycle's delay in fact. Imagine if the input comes along and changes just after the rising edge of the clock. Then the change at the input will not be detected until the next rising edge. So the output of our synchroniser is always going to be a delayed version of the input, and the amount of delay depends on when the input change arrives. If the input changes just before the rising edge, we're going to detect it very quickly. If the input changes just after the rising edge, we have to wait almost a whole clock period before we detect it's changed. So the circuit on the right-hand side must never assume that it knows exactly when the input changes. We have to design our communication protocols in such a way that this variable delay can be tolerated in our design. And if we have our design which can tolerate a variable delay, then we'll see later that it can tolerate that this first flip-flop might occasionally become metastable, just as long as this second flip-flop doesn't. Let's look at what happens if the first flip-flop does become metastable. So here our input changes right at the rising edge of the clock. This will cause the first flip-flop to become metastable. So we'll assume that Q1 and Q2 start off at being 0 again like before. This first flip-flop gets sent into a metastable state. Now, not that it matters too much, but we can assume that the same contamination period applies. And if we want, we can assume the same propagation delay period applies, although this is just an academic exercise. The thing we really care about is that the output of Q1 is going to be stuck halfway between 0 and 1. Well, it's going to be stuck at the voltage level, which is halfway between the voltage levels that represent a 0 and a 1 to be pedantic. So it's going to be stuck at its halfway value for a certain period of time. Remember, imagine someone's inside this flip-flop tossing a coin, and when this coin comes up heads, the flip-flop's going to exit from its metastable state. Now, it might exit to a 1 or it might exit to a 0. Let's assume here that it exits to a 0. So it's going to look like this. If it exits to a 0, then the second flip-flop here, well, at the first rising edge, the output of the second flip-flop 0 and its input is already 0, so it stays 0. At the next rising edge, we see that the first flip-flop's output has been a 0 just before and just after the rising edge, so the second flip-flop will also stay 0. At the second rising edge, what happens to the first flip-flop? Well, the input to the first flip-flop has been a constant 1 around the rising edge this time here. And so this second flip-flop is going to clock in a nice clean 1. So its output is going to change from a 0 through a period of uncertainty and become a 1. And it's going to stay a 1 because at this point too, its input is a constant 1. Our second flip-flop comes along and sees a nice clean 1 here, and so it's going to transition to a 1. And so in this example here, we see that our output looks just like our input signal. Here's our input signal. Here's a nice clean output signal. It's just been delayed this time by 2 clock cycles. So remember from the previous slide, our output is always going to be a delayed version. This time it still is a delayed version. It's just been delayed by an extra clock cycle. So metastability does not change the shape of the signal, it just can introduce an extra clock cycle's worth of delay. Now for completeness, let's assume that the flip-flop came out of its metastable state the other way round. In this case, that means that the flip-flop decided to exit here and exited with the value of 1. And so the difference is that the second flip-flop is going to see a nice clean input at this time period here, and therefore the output is going to be the same shape as the input, it just occurs a clock cycle earlier. So the only effect of metastability is to determine whether or not there is an extra 1 clock cycle's worth of delay between when the input changes and when the output changes. And that's the key message. Metastability for a single bit is not going to stop the design from working, it's just going to introduce a delay of 1 more clock cycle. But there will always be a variable delay, and therefore the receiver must be designed in such a way that it can cope with this uncertainty between when the input changes and when it sees the input as having changed. For completeness, let's look at what happens if the first flip-flop has not resolved from its metastable state after the first clock cycle. So that means that the first flip-flop gets thrown into its metastable state, and it's going to stay here up until the next rising edge. Now, because the input to this first flip-flop is nice and constant about the rising edge, the fact that it takes a photograph of a nice clean signal at the second rising edge means that it will come out of its metastable state no matter what and take on the correct value after the second rising edge. So it stayed in its metastable state. It didn't come out of its metastable state due to being randomly thrown out, which normally happens, but whenever a flip-flop takes a nice clean photograph of a constant input, it will come out of its metastable state no matter what. That's guaranteed. For our second flip-flop, we can assume that it started off 0. At this rising edge, well, I haven't drawn this properly here, the output of the first flip-flop doesn't become metastable until after the contamination delay has expired, and we're assuming that this design is sensible. This means that the contamination delay is sufficiently long that the output of the first flip-flop doesn't start to change until after the second flip-flop has had a chance to take a nice clean photograph. So the second flip-flop sees a nice clean 0 and stays 0 here. At the second rising edge though, the first flip-flop is in a metastable state, stuck between a 0 and a 1, and this poor second flip-flop gets this halfway voltage applied to its input, so it's going to misbehave. There's a good chance that it will become metastable. But here's the interesting thing. This first flip-flop has got a little man inside it tossing a coin, waiting for heads to come up. The second flip-flop has got another little man inside it, also tossing a coin. Now, the probability that this first flip-flop doesn't exit from its metastable state might be 1 in a million years. The second flip-flop is independent of it, so the chance that both these flip-flops are not going to exit within a clock cycle's period is going to be, I don't know, maybe once in a billion years or something. And so this is why if we were to add a third flip-flop to our design, the only way this design is not going to work is if this guy becomes metastable for over a clock cycle, and this guy becomes metastable for over a clock cycle. And the chance of both of them becoming metastable for longer than a clock cycle is much, 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 much lower than the chance of just one of them becoming metastable for over a cycle, and that's already small. And so that's why, if you're completely paranoid, you can actually add more flip-flops, and you will decrease the probability of ending up with a signal at the output here in the metastable state. By having 3 flip-flops, it means potentially, if things go bad, that we might introduce a delay of up to 2 additional clock cycles. But if that's tolerable, and normally it is, you're all but guaranteed that the output is not going to be in a metastable state. Now, some of you may have realized when we've been drawing these diagrams that if the input changes too quickly, it can cause problems. Now, an input changing too quickly relative to the receiver's clock rate is already going to be a problem, because if the input changes too quickly, we can miss pulses. For example, if the input has got a very narrow pulse that's narrower than a clock cycle, then if the receiving device samples the input first here and then here, it's not going to see this pulse at all. So firstly, if we want to detect all pulses, we have to have a guarantee from the sender that every pulse is going to be at least as long as a clock cycle. And if we have to worry about metastability, then possibly longer. The basic point is, in all the designs we're going to do, we're going to assume that the input changes sufficiently slowly that the receiver doesn't miss an input pulse, and that a double flip-flop synchronizer is going to work well. The last topic for this video is going to be explaining why we can't use our double flip-flop synchronizer twice to synchronize a 2-bit input. In general, this is a very bad thing to do. So if we had just a single bit coming in, it's fine to use a double flip-flop synchronizer. So what goes wrong? Well, we can demonstrate with a simple example. Let's assume that the transmitter here is sending us a message to the receiver. And of course, at any one time, the input can be 00, 01, 10, or 11. To make it interesting, let's assume that the left-hand side is the control room and the right-hand side is a missile control facility. When we send the message to fire a missile, that missile will fire. And we're going to say that 00 means to deactivate the system, 01 means to acquire lock, 10 means to launch, and 11 means to activate the system. Initially assume that our inputs here are both 0, that means to deactivate the system. So one input 0, the other input is 0. And then we decide to activate our system. So we bring up both inputs to a 1 at the transmitter side. So this becomes a 1 and this becomes a 1. But let's assume by bad fortune that this transition occurs very close to a rising edge of the clock on the receiver side, the clock that's driving these 4 flip-flops. And so this can cause either of these flip-flops to become metastable. In fact, we don't even have to worry about metastability. If these changes occurred right at the rising edge, then it's going to be impossible for these flip-flops to decide whether the change occurred just before the rising pulse or just after the rising pulse. And even if you believe it's possible, then due to differences in wire length, etc., it could be that one of these flip-flops saw that its input had not changed at the rising edge, but the other flip-flop saw that the input did change. In other words, it's very possible that this first flip-flop here did see that its input had changed at the rising edge, so it becomes a 1 here. Whereas this flip-flop here, it's thought that its input had not changed right at the rising edge, so it still continues to output a 0. Now at the next clock cycle, this 1 is going to be clocked through to the output, and this 0 is going to be clocked through to the output. And so at the missile site, it's going to have received the message 10. Now it's true that it only receives this message for one clock cycle. At the next clock cycle, it will receive the correct message 11, because at the next clock cycle, this 1 will still be here. This 1 will have clocked through to here. But the point is, there's been a clock cycle when the receiver has seen the message 10 and it launches the missile. And this is why you can never synchronize more than one bit of information using a double flip-flop synchronizer, unless your design has some other special feature which we'll talk about in a second. So to summarize, a single double flip-flop synchronizer is going to introduce a random delay. Depending on when the signal arrives, it might be detected at the next rising edge, or it might be detected at the rising edge after that. And that's not even considering metastability. If we do consider metastability, then there could be an extra clock cycle's worth of delay, as we've seen before. And so if we have a signal which is just 1 bit, then we don't care about exactly when it transitions, because we agreed it was impossible to tell when it exactly transitions, because we're only looking at it at rising edges of the clock. So our design has to work without knowing exactly when it transitions. That means that for a single bit of information, all we care about is the shape of the pulse. We want to be able to count how many pulses there are. That's all we care about with a single wire. But if we've got 2 wires, then we care about what both of them are doing at the same time. And the problem with a double flip-flop synchronizer is that it can introduce different delays between the first wire and the second wire. And that's what happened here. We had 0, 0, then a bit later we had 1, 1 at the input. But due to the random delay, we saw that one of the outputs changed before the other one did. And that caused us to get this spurious code 10 and launch the missile, when in fact the transmitter had never sent a 10. The transmitter was only ever sending a 00 or a 11. There are several solutions to this problem, but they all involve changing our protocol. We can't simply have 2 bits coming in and expect things to work. So solution number 1 we've seen before. We can have a separate wire that tells the receiver when it is safe to sample these 2 wires. And so then, when we're sending 00, we can load up our message 00, meaning to deactivate, and then say, put a 1 on this line here, telling the receiver that it's safe to sample the input, it's not changing. Then when we do want to change our input, we can bring this line down here, make a change to the input, allow a certain period of time for this change to propagate correctly to the other end, and then raise this line again, telling the receiver it's once again safe to look at the message that's been sent. That's the solution we looked at in earlier lectures. Now there's also another solution for this particular example here. In this example, there's a natural order that we're going to go through here. We're not going to go straight from deactivate to launch. Instead, the natural cycle of events is we might go from deactivate to activate. Then from activate to acquire lock, and then from acquire lock to launch. That's the natural sequence of events. And we can assume that we go in the reverse order. In other words, we're not going to go from launch straight to activate or deactivate. And so if we're prepared to introduce this constraint that we can only move to a neighbouring state, then we can rearrange these. So what we want is we've got deactivate, we can move to activate, we can move from there either back to deactivate or to acquire lock, and from acquire lock we can either move backwards to activate or move forwards to launch. And from looking at how this system worked, we saw that the only problem was when both bits changed at once. As long as a single bit changes at any one time, we're okay, because a single bit changes, there might be a random delay, but as long as the other bit's constant, it will stay the same value and we're not going to get a wrong message. We're going to see the old message up until the output changes, then we're going to see the new message. And so there's a coding scheme called the grey code that achieves just this. Only a single bit is going to change between these messages here. So we're going to agree that deactivate can stay 0, 0. Activate is going to be 0, 1, and notice how only a single bit changes between these two. Then for acquire lock, again I only want a single bit to change. So I can't have 1, 0 because then both bits would change. And I can't have 0, 0 because that's already being used. And so the only thing that leaves me is a 1, 1. And again, we see that between these two states, only a single bit has changed. And lastly, for launch, again, we only want a single bit to change, and we only have a single code word left, and things work out nicely. I can choose the remaining code word in such a way that only a single bit changes again. So by using this grey code, I can now go back to using this design here, but the transmitter has to promise to only move up or down this list here. The transmitter here can only change a single bit at a time. If they do that, then we can use a double flip-flop synchronizer. Otherwise, we need to use something more complicated, such as this ready line here.